My name is Ryan Nico, and I am here representing Collider, and we're a hub for tech professionals. We are trying to build, well, not trying, I shouldn't say trying. We are building a community with digital business innovation and tech leaders. And we bridge the gap between digital business and technology. And we are proud supporters of DetroitTechWatch. They bring awesome, like super knowledgeable people to talk to us every month. So we're always happy to just to partner with them, Onario and Steve, because I don't know, they're just everything that our company and our community represents. So these guys are awesome. Usually Onorio will tell a story about how he met the speaker, but maybe Dean, I can pass it off to you since you're our man of the hour, and you can tell us how you and Onorio met, and then, take it away and tell us about who you are.
Okay, I'm happy to do that. While I'm doing that, if I can do two things at once, let me share my screen so I can share the presentation. Let's see if this is going to work. It's looking funky. This will take a moment. I need to tell the Mac that it's okay for me to share my screen on Zoom. So just give me a second. But while I'm doing this, typing and talking, I met Onario he would do those Detroit weekend, like 1 day or 2 day conferences. Hang on just a second. Why isn't this coming up? There we go. And I spoke at one maybe 10 years ago now, I think. It was certainly before COVID, long before that. And I don't know that I've been back to Detroit since, but I'd love to come back sometime and see how everyone's doing, and see how the city's recovering from the travails, a decade or so ago. All right, so about this talk. I talked to Onorio about what he might be interested in having as a talk, and he went through some of my old talks, which you can find at this polyglotprogramming.com link. I've updated this one. There's actually an old version of this talk, but I'll post this one as well. But you can find all my talks there. And he picked this one, which is kind of interesting because this is actually an old talk. If you look at the copyright at the bottom, I started doing this talk like over 10 years ago, and really the last time was in like 2014 or so. So what I decided to do though is do the talk, but also I've added stuff that says, well, this has actually changed, or this is actually held up. So we can see where things were like 10 years ago, which is kind of the age of Hadoop, and where we are today, and then get into some of these questions about how this enables or is kind of in line with what we know about functional programming and so forth. Once again, feel free to ask questions at any time. Let's see, I think I actually have two screens. Yeah, I'll put the chat window down here. So if I see questions, I'll try to answer them as quickly as I can. And here's my email address if you want to follow up. You can also follow me on Twitter at Dean Wampler. I'm very creative in my Twitter handle name. There we go. Okay, so the first question is, well, what exactly is big or copious data? Well, I thought these DevOps Boric quotes were maybe appropriate. Big data is anything which is crash Excel, or big data is when it is fit in RAM. Big data, or small data rather. Big data is when it's crashed because it's not fit in RAM. So, which is not actually all that wrong what he's saying, but normally we think of big data as like something that requires like clusters of machines, many terabytes of space and so forth. Okay. Actually, I just did notice one question. Let me scroll through quickly. Yeah, somebody put, Ryan, thanks for posting the link to my talks in the chat.
You're very welcome.
Okay. So I think a better definition then is, and this was especially true like a decade ago when Hadoop was really getting popular, that big data was really anything that was just so big that it, like some of the traditional solutions we had, like the databases of that era, and even just some of the smaller cluster environments were either too slow, too small, too expensive, and it kind of drove a lot of innovation that led to things like Hadoop. In places like Google and Yahoo and other, if you remember Yahoo and other places, that really it kind of encountered this big data problem faster than anybody else. And there were kind of three trends that were driving this, but I'm going to make the point that two of the three are actually have been nuanced to some degree in the intervening decade. And the first one was that these data set sizes were just growing and growing and growing as people like Google and so forth collected data, sometimes data about us, which maybe we didn't necessarily want them to collect, but they were doing it anyway, and they needed some way to process all this data. Well, one of the things that's kind of happened since is we've sort of realized that it's not so much volume that's maybe the value, it's quality. So in a lot of cases, people still have a lot of data. They may still need clusters for it, but this idea of just taking all of your data and dumping it in some sort of so-called data lake, like a Hadoop distributed file system or HDFS, maybe that's not actually as useful as we thought, because you still have to figure out what to do with it. But nevertheless, a lot of this innovation, certainly in this time frame, was driven by data volumes growing. Another really interesting trend was the sort of NoSQL model of, maybe we don't really need to define schemas for everything. Maybe we should just dump everything in Mongo as JSON files, and then we can kind of parse it later and make sense of it. Well, that's actually changed a lot, even though there's still a place for this kind of unstructured data, as I'll talk about a little later. There's really been a movement back towards structured data as being most useful for most people. So this has been an interesting sort of cycle that we go through. There's a little bit of noise on the screen, so if you might go on mute if you're not talking, I guess. Now, this last one I think is still true, and that is that we have seen a tremendous, a lot of progress in applications of software that are driven by data rather than driven by specific rules that we program into it. And a famous example are things like self-driving cars. This happens to be a pretty famous one. This is like the second generation of a car called Stanley that was part of a joint research project between Stanford and Google. The leader of this is a professor at Stanford named Sebastian Troon, who's also a co-founder of Udacity, if you know that online learning company. But well, here's what's interesting. 10 years ago, those guys demonstrated that this actually worked. You could actually train models to identify pedestrians, identify roads, navigate things safely. And they actually had pretty much solved the problem 10 years ago. But it's a great lesson in what it takes sometimes to go from, sort of a research success to something that can actually be used in daily life. Because it's always that small percentage of failure that kills people, and that's really one of the reasons why we still don't have self-driving cars beyond just research projects like this. So it might still be another 10 years before they're ubiquitous. But anyway, a lot of interesting technology was developed, and this was even before a lot of the recent amazing stuff that was done with like neural networks, in fact. Okay. Let's see, wrong button. There we go. Another interesting thing that happened about this time frame, and it's worth clicking this link when I send you the slides, that there was a fight that broke out on the internet between Peter Norvig, the director of research at Google, and Noam Chomsky, the famous linguist. Chomsky is famous for this idea that our brains have structured formal grammars that we then sort of actualize in different languages. The language I'm speaking now, Chinese, all of these languages are kind of based on some fundamental grammar primitives that are in our brain. But what we've found out, and Norvig is certainly a leader and has been in this space, is that just by building probabilistic models that don't necessarily know the structure of language, we can do amazing things like natural language understanding, translation, just a lot of success in that way. So these guys kind of started fighting on the internet. And who doesn't fight on the internet, let's be honest. But anyway, they started fighting on the internet about these fundamental disagreements about the structure of language and how to represent it. It's probably true that there's some of both, that there probably are structures in our brain that are hardwired for language in some sense. But it turns out for the kind of applications we've built, using probabilistic models like neural networks is proven successful. Although you could certainly argue that even the most sophisticated neural networks that are now approaching hundreds of billions of parameters still don't have intelligence. they don't really understand what it is they're analyzing, unlike a brain. So there's probably something in the middle of both of these arguments that's true. Anyway, it's a pretty interesting thing that was happening at this time. Here's another picture of the bean in CloudGate in, I think it's CloudGate, Cloudveil, I forget which. Let me take a little trip down down memory lane and talk about Mapreduce a bit. This is kind of old school Hadoop compute model, but it's kind of indicative of sort of initial attempts to build a general purpose compute tool for big data that only got so far and then was replaced by much better tools. And so it's a good way to kind of see the evolution as we build up to this idea of functional programming as being an ideal tool. So this is the slide 10 years ago. Hadoop is the dominant Copious data platform today. You know, we can say now that it was at the time, but you know, it's no longer the dominant platform. But the big pieces of Hadoop were this model of compute called Mapreduce, the Hadoop distributed file system where all the data was lying, and then stuff to manage resources. So this is roughly what a Hadoop cluster looked like schematically. And this is not that different from clusters that the way Spark actually organizes itself and a lot of other distributed compute systems where you have like masters, maybe in some federation so that if one fails, the other one can take over. Hadoop had a thing called the job tracker, which kept track of the work you submitted. The name node was sort of like the metadata about where all the data is in your distributed cluster, which is these nodes in the bottom, just a massive pile of disks, and then local services that handle tasks that are part of the jobs, and then the data and where the data is actually located on hard drives. So this is schematically what a Hadoop cluster has always looked like. Even today, if you buy a modern Hadoop cluster, people still do that. But let's actually see how you would do a typical algorithm kind of conceptually working with this paradigm, this kind of structure that I just described. And it's the inverted index. So what this is like a very simple search engine. The inverted index would be, I have documents and the documents have words, but what I want to do is actually find the words and then create links to the document. So if I search for the word Hadoop, it will, Google or whoever will show me all the documents where that word appeared and so forth. So that's why it's called inverted, because I started with documents. Now I'm going to extract the words and go to an index of words to documents is the idea. So imagine I've got web crawlers. They're going through Wikipedia at the moment. They're finding the Hadoop page, the HBase page, which was the database at the time, still exists, I guess. And then a SQL engine Hive they'll actually come back to a little bit later. And it builds up this initial index of all of these big, gigantic files in blocks. So, and that's actually the storage. The file is actually a block, but it has this sort of virtualization as being, a massive multi-terabyte file or something. And all it has is like the URL and then the content of the file, maybe cleaned up, like removing HTML tags and stuff like that. And then we pass it into something called a map task. And here we are, Mapreduce, right? And what this thing is going to do is some magic where it basically tokenizes all the words, and it's going to spit out these tuples of like word and URL combinations. And then it goes through this process of shuffling this data over the cluster, because what do I want to do? I want to get all of the tuples where the words are the same, like all the occurrences of the Hadoop. I want to bring all these together in some node somewhere for this reduced task. And then I'm going to do the final count and final index of for all occurrences of the word Hadoop. Here's all the places on the internet that happen to have that word. And that's what the reduced task does. It gathers all of these tuples and here's what the tuples look like actually. So for Hadoop, I've got one occurrence on this page. I've got one occurrence of the word provides, which is what I had in the example here, and so forth. So this is kind of what the tuples might look like. And then the reduced task is going to collapse all of the common occurrences of Hadoop into a list of here's one URL and its count, another URL and this count. And you can see what that looks like on the right. And that's my inverted index. Once again, blocks are like the kind of internal structure that they're the actual physical files on the hard drives, but I have this virtual file that's a giant inverse index. So the idea, and these are kind of getting to the functional aspects, map, and really this is not map, it's actually flat map. This is the idea that I take one input, and for each of those inputs, I'm going to output 0 to n things. And in our case, one document, it's full of words, so I'm going to output, if it's an empty document, nothing, that'll be 0. But if assuming it has words, then maybe say 1,000 of these pairs of the words, and then information about the location. And really, that's technically flat map. The difference between map is supposed to be 1-to-1, like one input, one output, always. And flat map it's really a fancy way of saying I might put out a lot of them, but there's this sort of flattening process, so I don't get like nested collections of things. I just get one big collection of those tuples that I showed you. And that's where the word flat comes from. But it's a more general situation than map. And then reduce is really, like the word says, I take multiple inputs and collapse them into one output. And that's what we've done, multiple tuples with the word Hadoop or provides or HDFS, and then collapsed each of those groups into one thing, a final record with the word Hadoop, and then a list of those URLs and so forth. So that's really the gist of what Mapreduce does. And if you can squeeze your algorithm, whatever it is you're trying to do, into this map phase and reduce phase, then good on you, because that's what you've got to work with, whether it fits you or not. And in fact, it doesn't really fit very well for a lot of algorithms. This is Lake Michigan frozen one day a long time ago. It does this every now and then, and when we get a good cold spell. It's my token romantic beach scene, as you can see, obviously, from the couple in the lower corner there. Okay. But it's just actually really hard to program Mapreduce. It was a pain. You really had to be a developer. If you were a data analyst, you were screwed. There was no way that you would have the tolerance to learn how to write this algorithm or use this API. It's also really coarse-grained, just a lot of details that you had to manage. You couldn't express things in the way that you thought of them. Like, if you conceptually think about that inverted index, the way I walk you through it, you'd like to somehow translate that mental picture in your mind into code in some reasonably simple way. You cannot do that in Mapreduce. So in fact, you get one map and one reduce phase, and then the job finishes. So if you can't actually do everything in that, that very limited thing, you might have to sequence a bunch of jobs together. And then you hit a terrible efficiency problem where you end up flushing lots of data to disk between jobs, because there's no sense in which work coming out of one job is going to be used by the next. This is a problem Spark solved for us very well. The other thing it's not very good at, it's really designed for massive batch mode processing. And if you want to do something with low latency, like processing streams of events, it was just not a suitable tool at all. Whereas Spark has actually been adapted for that purpose, for example. And finally, it was the Java API that was really hard to use. I'll just show you an even simpler algorithm, which is word count. In this case, I'm going to forget the URLs. All I care about is how many times did I see the word Hadoop, how many times did I see HDFS, and that sort of thing. It's kind of the hello world program for big data. So we tokenized the documents as before, but then we'll just forget about the document locations and just return the, basically count up all the words. And this is actually the whole program. So it's deceptively short. The stuff we care about, which is actually the business logic, if you will, is right here. And so, if you're a Java programmer, then you could get your head around this reasonably well. There's a lot of ceremony and stuff here. All the rest of the stuff that isn't circled is just kind of weird API ceremony I have to do. And in fact, when I saw this API and started working with it, which, it just becomes overwhelming when you're doing something more complex than word count. It reminded me of something that maybe none of you actually did, but back in the 90s, we had this API called Enterprise Java Beans, where there was, your business logic just got lost in all of this framework and ceremony and stuff. And it was actually not a very good API to work with. And the same is true here. You just get totally lost in all this stuff when what you're really doing is actually conceptually simple. There's a better way we can do this. Raise the light here a little bit. All right, so just to throw in some closure for those of you that know Clojure, here's the shortest program I've ever seen for word count. And this is using a library called Cascalog. It's probably still around, but I haven't really kept up with the Clojure community. but it basically leverages the fact that there's some logic in this API, and we can actually use a logic language, which is what this is based on, to do word count. And here it is. This is like the whole program for word count in this. If you've heard of data log, which some of you may have studied in computer science, it's based on that logic model. I don't think I can actually describe the syntax. I don't really understand exactly what all the operators and symbols are doing here, but just to prove that you can write very concise programs if you know how to map this logical thing I want to do to something, in this case, that happens to be a logic style program. I'll show you something that's a little bit more intuitive using Spark here in a second, or similar APIs. So let's actually do Spark. Chances are most of you at some point or other have played with Spark a little bit. It's still really big, as you know. And this is actually the way to write this algorithm in at least the original Spark API. You can actually do this in Spark SQL. I'll come back to that a little bit later. But what I'll take the time to walk through this. This is Scala Syntax. So in case you don't understand that, I'll explain a few of those details. But I have one import statement, like in Java. In Scala, you can declare singleton objects. So I really only need one object that has my main routine. That's what the next two lines are doing. And I'm going to pass in a list of arguments. I'll use that list of arguments as where the files are located to process. So the first thing I'm going to do is create one of these Spark context objects. And then I'll take whatever the first argument is as my list of files to process. Then I just, what I do next is this text file thing is going to return all of the lines in these files. So the next thing I'm going to do is the equivalent of that map operator that I did before. Now it's called flat map because that's really what it is in functional terms. And I'm going to, as a naive, simple assumption, I'm just going to split on white space. So this regular expression here with the split function call. And the underscore just means, all right, take the line, just treat it anonymously. It's the first argument to this function I'm passing to flat map. So for each line, split it on white space, not really what you should do, but good enough for our purposes. And then the next step is actually a map. I actually got the indentation a little wrong. This dot map should be at the same indentation as flat map, and you can see that with the parentheses ahead of it. But so what the splitting does is now I just have a stream of words coming out. So now I just can do a one-to-one mapping between each word and a tuple of a word and a count of one. So I've seen a word once, I'll output a tuple. I have this nice syntax in Scala for these little concise data structures. Just wrap it in parentheses. Now I've got a word and a count of one. And then reduce by key is a nice method that just says, take all of those things in the first position, all the words, join those together, and then apply this function, which is doing addition on the things on the second end, the ones. In other words, it's bringing all the words together that are the same, and then counting up all of those ones to determine the full count for each one. And now I've got a tuple of unique words and then a count of 1 to n, whatever the n happens to be, and then I can just save it as text files. Hopefully you sort of follow the gist of that. But here's a first example of where a functional programming is really, really powerful, because I can conceptualize the steps that I need to do from the input of this arbitrary text to the output I want, which is a list of words and counts. And then if I know these operators, like how flat map works, the idea of splitting stuff, and how that's actually just kind of a Java API, the regular string split method, but still something that I can combine together with these other things. Reduce by key, which is just a simple way of not having to deal with the tuple. It just says, grab the first thing, treat that as a key, and then apply the function, which is this underscore plus underscore to what's left. Those are all integers, so I'm just adding integers. And then save as text file is unique to Spark. If I showed you the Spark code, and I have a deck on my Polyglot programming site where I actually write inverted index in Spark, and I think it's just a beautiful, beautiful example of how when you have these things I'm going to call combinators, these little operators that are in your mind, then it's really easy to take conceptually what you need to do and turn it into step-by-step transformations to output what you want to output. While I think about it, let me comment on the question about object-oriented programming versus functional in terms of performance. So Scala is running on the JVM, so underneath there's a lot of objects. In fact, each of the outputs of these functions, at least in the naive way I've written it, is going to create an object that holds like each of those tuples and holds like the initial document and all that stuff. Now Spark actually does some what they call pipelining, where they'll combine things so that you don't create as many intermediate objects. But in a way, this code might be actually slower than the Mapreduce code because I've actually taken more steps to make it more conceptually simple to understand. So there's a risk that there might be more object instantiation in the middle as I do stuff. I wish I had time to talk about what Spark Sql has done. I'll talk about Spark Sql in a minute, but if you think about Sql as a dialect, it's a beautiful boundary between conceptually what I want to do as someone writing a SQL query and stuff that's going on under the hood to manipulate my data and give me the result I want. And they have leveraged that sort of separation to do incredible optimizations internally. So if I rewrote this in Spark Sql, it actually wouldn't be working with things a piece at a time. I'm actually telling it, for each line, do this, then do this with each word, then do that. Instead, I would sort of express, as a relational query, here's the stuff I want you to do. And then it can actually optimize how things are laid out in memory, how it orders computation and so forth. And it can, as a result, the Spark SQL system, I guess, if you want to call it that, is orders of magnitude faster than this API because of these kind of aggressive optimizations it can do when you don't try to control it quite as tightly as I'm doing here, but you express the computation you want in SQL, and then let the optimizer figure out how to do it behind the scenes. Anyway, hope that sort of made sense. All right, so what happened, again, 10 years ago, when people saw Spark, they were like, hallelujah, our problems are solved, we can stop using Mapreduce. It was a much more flexible compute model. At the time, it was often 30 times faster than Mapreduce for most algorithms because it was smart about not writing stuff to disk when it didn't need to. And now the number is actually considerably greater for the reasons I just mentioned if you use the SQL API. It's probably 100 to 1,000 times faster. And it came out of Berkeley research where they were trying to build a compute engine to do machine learning, which has even more flexible compute requirements than just like data processing, like a lot of very fine-grained iterative computing that's sometimes required. So that's where this emerged. But it turns out SQL came roaring back. So even before Spark came along, Facebook had already written a tool called Hive, which was a SQL dialect that would actually just translate your SQL into these MapReduce jobs. So it wasn't necessarily faster, but it was a lot easier to use if you knew SQL and you could express your problem as SQL. And the same thing has now happened with Spark SQL. It's by far the dominant way that people write Spark. Turns out the Python API for Spark is #2, even though Spark itself is written in Scala. And you may have heard of Impala and Presto that are other data compute systems from Cloudera and Facebook. Impala's Cloudera, Presto's out of Facebook. So it turned out that was extremely popular because a lot of the people who wanted to work with Hadoop and work with this data were data analysts, and they already knew how to write SQL. So if you could give them a SQL dialect, even if it was weird in some ways and limited in others, that was just really great because that Java API was just way beyond what they were willing to do. And then Spark did the same thing. It layered on top a SQL dialect on top of its core engine, and then it basically replaced the core with a highly optimized SQL optimizer that does things like better layout in memory of objects so that you get much more efficient memory access. And the same thing basically happened with these other tools. And I'm only listing a few of them that still exist. There's a whole bunch of other tools in this category that have kind of disappeared. So it turns out in the Hive SQL dialect, you can actually write word count. There's a few additions to SQL here, like notice this load data in path. They've added hooks like I don't actually have a SQL database where everything's a big black box. I actually still have files somewhere, so I need to tell it where to go to find them. But I'm going to create this table with just one schema, sort of a virtual table that just has the lines that I'm going to read. We'll call that docs. And then we'll load data into that. So now I have this kind of virtual table idea. And then I'm going to create my final table of output, which will be the word counts. And there's just a few, maybe custom built-in functions here, like explode and split. Those might actually be in regular SQL, now that I think about it. But if you know SQL, you ought to be able to look at this and intuit that, yeah, this is basically that algorithm, but it's expressed as SQL. So if you're a real SQL guru, you could do word count without having to learn even Scala or Java or Spark for that matter. You could just learn SQL, and that's some weird dialectical additions. So in fact, even at 2014, when I was doing this presentation at conferences then, SQL was already roaring back in terms of popularity. And the other thing about that was people recognized that we do need structured data. It's actually more convenient to have sort of a relational model for our data. So let's talk then, let's go back to functional programming and talk about this idea of combinators. These are those functions like flat map, split, and so forth that I was describing that I can compose together, combine as it were, to build up a transformation that I want to do in a conceptually easy way once you kind of understand how these combinators work. And they're really why Scala and Clojure, and to some sense even SQL, which has kind of a restricted subset of these, why they were so appealing and why they allow you to write such concise code, because they really are the kind of ultimate goal we have in software, which is give me stuff I can compose together. So when I build an application, I don't have to write much. I just kind of logically compose things and sort of very close to the way I'm thinking about the problem without having to dive down into a lot of detail. And it kind of reflects the fact that most data things that we do really represent mathematical transformations, like summing stuff, computing statistics, or whatnot. And hence, if we can think about a little bit about mathematics from what we remember in school, let's say, then we can really apply that to a lot of the problems, especially if the libraries or the languages we're using give us those kind of primitives. And there's this nice post here that where Evan Miller talks about this idea. So to define combinators a little bit more precisely, they're basically functions, but they're functions that don't have side effects, meaning they're not going to write to a database. They're not going to call the logging system. I can compose them together without worrying about sort of collisions with the rest of the world that they might be doing that I'm not aware of. They just take what I pass to them, do some work, return results, and then forget about it without any kind of side effects, as it were. And that makes them really easy to combine. And in fact, it really was kind of the idea for the original relational model. It was based more on set theory and first order logic, but it was this idea that we can structure things and then ask questions of them, run queries in a logical way, where we organize data as tuples, was the technical term, grouped by relations. And we still use the term relational today. Although most relational databases really kind of departed from this model for reasons I won't get into. Nevertheless, you'll see a lot of the stuff that I described earlier as SQL operators. So let's look at that a little bit. So for example, if we go back to our word count, where I created this table that had a character and an integer, using SQL syntax. That's kind of similar to defining a stream of tuples in a language like Scala, and Java has something similar now, for example. But both of them have a schema. In this case, it's this thing in the square brackets that's a tuple of string and int. It's a little bit more verbose, but maybe clearer in the table definition above. I want to restrict the output. I'm using the term restrict in kind of the original COD sense of the word, where I only want to see word counts for the word Chicago, which actually just returns one word in this case, because that's the single key. But I can write this as a SQL query. I could also write this in Scala syntax. The case thing, all that does is it's a way of destructuring my tuple into a word and a count without having to do it in some other way. So it's a really convenient syntax in Scala to tear something apart into its constituents. In this case, I want to filter, but only return the tuple when the word happens to equal the word Chicago. But already you can start to see how Sql is more concise than even Scala, which is a really, I think, nice functional language. And that's one of its powers, is you can very concisely express things. We'll see another good example of that in a minute. Similarly, I could, just select a column, and in kind of adapting the previous example in Scala, I would just, extract the word in the count and just return the word, and that will give me a new table, quote unquote, that just has the words in it. And this is the example I mentioned. If I want to do a group by, you write enough Sql, these become kind of second nature about, grouping by the count, ordering by the size, descending, so I can see the most frequently occurring words is what I'm going to see in this output. I can do that with Scala, but it's a little bit more involved. And as I said a minute ago, if I write this query in Spark SQL, it's probably going to be a lot more efficient than if I write it in the original Spark Scala API, where I'm kind of telling the system what to do rather than expressing my desires and letting the system figure it out for me. And if you actually ran this, it would look something like this, where if I input these tuples in a list, like A and 1, B and 2, and so forth, and then run through this group by statement, then I get something like I have at the bottom here. I think this is what I meant. Yeah. Okay, but I hope you get the point. I've just shown you a few of the basic Scala functional combinators like map, flat map. We did filtering, that's another one. And reduce, we talked about that as well. And we often find these in Sql, which is kind of a reduced subset of functional programming. And we like doing it a lot in these functional languages as well. Someone asked or mentioned in the chat that machine learning is more math than coding. I'll come back to machine learning in a minute. I'll talk about that. There's some interesting nuances to that, I think. Okay, so why would you choose Sql, say, over a functional programming language? Well, Sql really is optimized for data operations. Query optimizations can be amazing, especially in a tool like Spark, and when you compare its API options. But you are a little bit more limited in what you can do. FP, unlike Sql, functional programming languages that are Turing complete, they give you more combinators to work with, and you can define arbitrary functions more easily than you can in most Sql systems. So I would argue, and this is literally the kind of thing you see in downtown Chicago, these heavy lift helicopters sometimes coming on the weekend. They're flying like below eye level, and what they're doing is they're like picking up new refrigerating or HVAC units and plopping them on buildings. So I forget which building this was. It might have been the one that you see in the foreground, but literally, if they would need to replace the HVAC system on the top of a building, the easiest way is to use one of these helicopters to pluck the old one off and plop the new one on top, and with some guys standing around to make sure nobody gets hit by anything. But it's kind of freaky when you see this helicopter dropping below eye level and between the buildings on the street. Anyway, that's where this picture came from. So let's talk a little bit about functional programming then. Well, so here's what happened though. Back in the early 2000s, people were talking about functional programming because we kind of realized that Moore's law had run out of gas, that the only way we're going to be able to keep scaling compute was to go distributed. That means everybody suddenly had to learn how to do concurrency and distributed computing. And it turns out that one of the features of FP that I haven't mentioned yet or kind of alluded to actually, is that it really emphasizes doing things without side effects, without mutating existing state, but instead taking a state and returning a new state. And that turns out to make concurrency programming much, much easier, at least on a single machine where you're sharing memory. And so the claim at the time, again, mid-2000s, was that functional programming was interest in it was being driven by this concurrency multi-core problem that everyone needed to solve. And that's how I got interested in it initially, and it certainly did drive a lot of interest. But I think, in fact, what happened was I made this claim 10 years ago, and I think it turned out to be true. Although I don't want to claim that I'm some genius about this, but nevertheless, there's a lot more data programmers in the world than there are people writing concurrent software. And data really was what drove interest in functional programming. And that's pretty much turned out to be true. And it's really just a question of numbers more than anything. I will mention some comments here. Anthony posted a link to his Gallia library, which I'm really anxious to try. I just haven't had a chance to do it. It's a Scala library that goes beyond the built-in collections in Scala to do more data kind of manipulation calculations. So it looks like it's a lot of fun to work with. And I'm nearly done, but I thought I would finish with just a postscript that I added today that wasn't in the original deck to kind of summarize what's changed in the last decade or so. Excuse me, let me get a drink here. First of all, the whole idea of data lakes and Hadoop has kind of become passé, in part because people realize that standing up big clusters that are kind of expensive and hard to maintain and just dumping all your data in them didn't necessarily deliver a lot of value in the end. They needed to be a little bit more strategic and maybe deliberate in how they work with data to try to get value out of it. And as I mentioned, Sql, even though it was old and people were kind of poo-pooing it and just like, oh, that's old stuff, we don't do Sql anymore, it turned out it really was still very, very useful. We just needed to figure out a new way to do it. And so it is, come roaring back as one of the most important ways that people work with data, big and small. And it also highlights the fact that structured data is a lot easier to work with. It's hard to get the structure right, as opposed to just like, say, dump everything as JSON in MongoDB, but it gives you so many more benefits down the road of just more precision, more control over what you have, better understanding of it. And you get all the benefits of SQL databases that you often lose with some of the NoSQL databases, like very optimized joins and group bys and so forth. It can be hard to implement, or it may not even be provided by these databases, and you end up writing code to do what you should be doing with your database instead. That doesn't mean that NoSQL databases are dead. They're still used, but people are just learning how they should be used, not just treating them as a solution to all problems. So they still have their place, I think, for sure. And it was this interest in SQL is really what drove the Spark community to embrace SQL itself and really kind of drive all of its innovation through that API. The old there is actually an R API, but what I meant is the old reduced, or what was it called, RDDs. I can't remember what the word R was. Anyway, the old model, the old API that I showed you is still there, but it's really not how most people should work with it, because the SQL API is usually more concise, and it's also dramatically faster than the old API, because it creates a great, as I said, a great boundary between the optimizer underneath and the ideas you're expressing in the SQL. So it really is the way to go when you're writing most jobs. The other interesting trend is taking data lakes and actually making them more structured so they easily accommodate things like indexing, which is something else we really like from SQL. So Databricks and the Spark community developed this Delta Lakes concept that is kind of a new take on a data lake that gives you more structure and more facilities that you can leverage from your SQL. And it's also driven a renewed interest in data warehouses. People realize that data warehouses are really fantastic for what they do, but now they're exploring new ways to do it, like in a cloud-based system like Snowflake. And Snowflake itself has now become an ecosystem. I think it's interesting to compare these two. If you pay attention to this space, you know that Databricks, the guys behind and gals behind Spark, and Snowflake are like mortal enemies right now. They're like really competing for customers because they do overlap a lot. I think Snowflake is great if you really do come from kind of a traditional data warehouse world where everything is nicely structured as SQL, because it gives you all of those benefits. Plus, this ecosystem lets you leverage tools like machine learning. But if you have a more heterogeneous world of data where you do have some unstructured data, you do have structured data, then maybe Spark and Delta Lakes is the model you need. It's kind of my take on that. But there's still a place for semi-structured and unstructured data. A lot of the success we've had in machine learning and AI is about making sense of that kind of data, finding objects and images, taking a corpus of data and understanding, in quotes, what it means, or translating it from English to Chinese or something. This is still a place where this kind of data is useful. But even in this case, if you think about it, if I'm doing a translation, or if I'm extracting like a summary of a big Word document or something, I'm actually extracting structure from this unstructured data. Certainly, like picking objects out of images is a good example of turning unstructured data into structured data. So even then, we still find that we really want some structure at the end of the day. Now, here's an interesting thing. It's a bit of a sad thing for me. I hate to end on a sad note, but as much as I love Scala and all the functional combinators, Python has really emerged yet again. Another thing that's kind of been resurgent is Python is probably the most popular language now for writing applications in machine learning and AI. Even though the Python language itself and the libraries don't really give you the same power and functional combinators that you find in languages like Scala and Clojure and so forth. And the reason for this is actually pretty simple. Most of the people writing these kind of apps aren't really regular software developers. They're like data analysts or data scientists who know enough programming to get their work done, but it's not their passion as much as data is their passion. And what they're working with are these very powerful libraries, some names like Pandas and PyTorch and TensorFlow, where they really don't write a lot of Python code. They mostly are manipulating their data through these very big libraries, many of which often have C kernels for performance. But they're basically giving up some of this functionality that I described as so powerful and exchanging it for libraries that are more customized for the kind of data analytics that they want to do. Yeah, so it's kind of an interesting thing. I'd still rather use Scala personally, but I often end up using Python for various data apps. And I'm hoping that tools like Gallia might kind of reverse that trend a little bit. There's certainly a lot of passionate Scala data scientist types out there, especially in big companies like Stripe and Twitter, where they really have such massive data that the performance of Python is a concern for them at times. Still, though, I think if you talk to people who are writing pipelines for ingesting data, like ETL kind of things, Scala is still pretty popular for that, especially like the Spark API, because oftentimes you just need a lot of flexibility. It's complex enough that you need the flexibility of a language like Scala. You like having the functional combinators, and you like the performance of stuff running on the JVM when it's running, after it's warmed up and so forth. Yeah, somebody mentioned Scala Pi, which I actually know the guy who wrote this API. It's a really cool API that lets you talk to Python libraries from Scala. Once again, it's one of those I really haven't had a chance to try yet. But if you love Scala, but you're working with, say, PyTorch or something, it might be a way to kind of get the best of both worlds. Okay, so that's pretty much it. A little after 7. I appreciate everyone's attention, and I'm happy to take any questions and criticisms or whatever after that.
Please feel free to come off mute, off video, or I can read this. Anthony says, what are your thoughts on, forgive my, Kotlin?
Yeah, Kotlin, yeah. I think it's Kotlin, actually. Correct us both if we're wrong. Yeah, so Kotlin's an interesting language. For those of you that aren't familiar with it, it kind of looked at Scala and said, that's too complex. Maybe we can find some middle ground between Java and Scala that gets a lot of the benefits of Scala without some of the warts and the complexity. Scala is a great language if you really love programming languages and love getting into the nitty gritty and doing very powerful things with very powerful features, but it's not everybody's cup of tea. So I do think that Kotlin is, I would personally rather, if I had to pick between Kotlin and Java, I would certainly pick Kotlin. It's also getting a huge momentum now that it's kind of the standard language for programming on Android. So if you're an Android developer, you've probably used it. Someone mentioned Krangle. That must be a data library in Kotlin for data manipulation. Is that right? Yeah, okay. And once again, I just don't know the Kotlin space very well, but pragmatically, I understand why it's popular, and I certainly couldn't criticize somebody for using it rather than using Scala. Any other questions, comments, criticisms, complaints?
Don't be shy.
Don't make me calling people. Thoughts on Beam? So Beam is really interesting. Yeah. So Beam is a Google API that's primarily oriented towards stream processing, but tries to provide enough semantics that you could actually reproduce accurate computations. What does all that mean? Well, let me give you an example. Suppose that you have a dashboard. You work for, let's say, I don't know, maybe the Gap or something, and you have all these physical stores, and somebody in sales has this dashboard where they want to see, like, how many pairs of jeans am I selling in every single store per hour or something like this. So I want this data fairly quickly. Like, as soon as an hour hits, I'd like to see the new number for all of those stores, all of those different types of SKUs, basically. Well, if you think about how that would work, I could have the data streaming in from all of those stores, and I could do the calculation as soon as I hit 7 o'clock, 8 o'clock, whatever. But there's actually a problem with getting an accurate count, which is the data's in flight. So I could maybe wait a few minutes and hope the data's already arrived. But somewhere in the world, there's going to be some internet outage. There's going to be some machine that's being rebooted or whatever. So I'm going to have data arriving late. And that means I could either just say, all right, well, this is just a dashboard. It doesn't have to be 100% accurate. I'm just going to put a little notice that, final numbers not shown. This is just an approximation or something. The idea with Beam was really pushing the envelope to say, is there a way we could actually define semantics that would let you do the kind of exact counts, like the sort of things you could feed into an accounting system, that you could actually use to, report to the government and, taxes and shit. And what they've done is they've added primitives to let you say, all right, let's I want to do this calculation every hour as I described, but when data arrives late, I want to send a correction in this particular way, in the same way I might enter a correction in an accounting ledger. So, in other words, they ask the questions: what would it take to do something as precisely as I can do with batch data, but doing it in a streaming context where some data might be late? How do I handle that? How do I let people express how they want to handle those situations? That was kind of a long-winded explanation of what Beam is. I think in practical terms, it's most used with a tool called Flink, which is a wonderful streaming engine that I think the way it works is you can actually write your programs in Beam and then use Flink as the runner, or you can write in the Flink API. So if you really are into stream processing and you want to do kind of similar things to what we described, but in a very time restricted manner, then a tool like Beam or Flink would be the way to go. Okay. Now, somebody reminded me of the question, what about functional programming versus object-oriented programming in terms of performance? I got into this a little bit. One of the benefits of functional programming when you're using those combinators is that you can break down it mentally. What are the steps of transformation I need to do, and then write them down the way you thought of them, kind of the way I did word count and so forth. But that may not be the most efficient way if there's no sort of pipelining of those intermediate steps to avoid creation of all those little intermediate objects. It could actually be slower than something that's maybe written with another language where I just kind of do everything at once and glom it all together and don't try to do this decomposition. So that's sort of a trade-off you make. The great thing, though, about tools like Spark is when you use the same operators in Spark, most of the time they actually do pipeline together into one task a bunch of those steps. So they actually eliminate that performance problem for you. So you get the best of both worlds. Other than that, though, it's usually a good idea to think about what's happening under the hood. So I'll just give you one other example, not to belabor this question too long. And I see it was actually about programming speed. I'll get to that in a second. But one other thing, suppose I have a big data structure and I want a new version that just changes one element right in the middle. In an object-oriented program, I would probably just reach in and change it, and that's going to be very efficient. The problem is if other people are working with that data structure in shared memory, then I might completely mess up their work because suddenly it's changed and they didn't do it. Where did this come from? So in a naive approach of functional programming where things are not mutated, I would make a big copy of that whole thing, which is, terribly inefficient. But it turns out there are algorithms or data structures is really the right word, where I can make a copy where I share all the structure that hasn't changed and I only just make new bits of it to represent what's different. And each of those people looking at the original data structure still see what they've always seen, but the person that wanted that changed data structure now sees a pointer to a new thing that then has the change, but then shares all of the other unchanged stuff with everybody else. Don't know if that made a lot of sense the way I hand waved that, but that's one way in which treating functional data structures as an abstraction lets us then do optimizations that work around problems inside. As far as programming performance, I really believe that once you learn these functional combinators, I just find I'm much faster writing Scala than I ever was with Java because I just naturally decompose problems in my head this way. The other thing that you do in functional programs is you think more about the state in kind of a precise way, and also the schema of your data, or like the objects, and what should be an object, or maybe what should just be a collection of random stuff that I don't necessarily want to encapsulate in objects. This is a hard question to answer just kind of in this way, but I do think that I write better quality code, I write it faster, and I write smaller code when I write functional Scala versus like object-oriented Java personally. But it's also because I invested the time to learn how to do that as well. Okay, other questions? Let's see, maybe I'll make sure I scroll down. All right. Well, I appreciate your time. Once again, you can find an old version of this talk at polyglotprogramming.com on that slide/talks. And I'll upload tomorrow probably this newer version that I have here after I do a little cleanup on it. And feel free to reach out also to my email or Twitter accounts.
Got it. And I'll include all your info in the follow-up to everyone, if that's cool, Dean.
That works for me. Thank you.
All right. Well, yes, thanks everybody for coming out tonight and listening to Dean do his thing. See how I rhyme there. And please stay tuned. We will follow up with a video as well as just links to the Collider community, because if you all want to join and listen to more talks like this, we'd love to have you. And yes, all right, Anthony, thank you. I will post your article that you wrote in Towards Data Science in the follow-up as well. Let me copy and paste that. But yeah, so everyone have an awesome evening. Thanks again, Dean, so much. And look out for an email from me, Ryan, from altimetric.com. And yeah, you all have an awesome evening.
Thanks, everyone. See you soon.